Grignard Metathesis, GRIM, polymerization, mechanism, control, and recent advances. Grignard Metathesis, GRIM, polymerization is an important synthetic method for producing regioregular π-conjugated polymers, particularly poly,3-alkyl thiophenes. The method enables precise control of molecular weight, narrow dispersity, and high regioregularity, which are critical for electronic and optoelectronic applications. GRIM polymerization was developed in 1999 by the research group of Richard D. McCullough and represents a major advancement in the synthesis of conjugated polymers. The process involves the formation of organomagnesium intermediates followed by nickel-catalyzed cross-coupling polymerization, often described as Kamada Catalyst Transfer Polycondensation, KCTP. This video outlines the principles, reaction mechanism, structural control, and recent advances in GRIM polymerization, with emphasis on the synthesis of regioregular poly,3-hexylthiophene and its applications in organic electronics. Π-conjugated polymers are central materials in modern organic electronics because of their semiconducting properties, solution processability, and tunable electronic structure. Among these materials, poly,3-alkyl thiophenes are particularly important because they combine high charge mobility with good environmental stability. Early synthetic routes produced regioregular polymers, which exhibited poor electronic performance due to structural disorder. Improved control over polymer structure was achieved through transition metal catalyzed cross-coupling polymerization methods. A breakthrough came with the development of GRIM polymerization by Richard D. McCullough in 1999. This method allows large-scale synthesis of highly regioregular poly,3-alkyl thiophenes under relatively mild conditions, typically at room temperature. The polymer most commonly synthesized through this approach is poly,3-hexylthiophene, a benchmark conjugated polymer used extensively in organic electronic devices. Regiochemistry and poly,3-alkyl thiophenes. The structure of poly,3-alkyl thiophene depends strongly on the orientation of adjacent thiophene rings. Because the thiophene monomer is asymmetric, coupling can occur in three ways: head to tail, HT, head to head, HH, tail to tail, TT. The sterically crowded 2 position of the thiophene ring is typically referred to as the head, while the 5 position is called the tail. Among these configurations, the head-to-tail orientation produces the most planar and electronically conjugated structure. Therefore, achieving high HT regioregularity is essential for high charge mobility and improved optoelectronic performance. GRIM polymerization selectively produces HT-coupled polymers, leading to highly ordered materials suitable for electronic applications. Development of GRIM polymerization. Before the development of GRIM polymerization, several methods were used to synthesize poly,3-alkyl thiophenes. Early work by Kenneth Elsenbaumer in 1986 used nickel-catalyzed coupling of diiodothiophene derivatives, producing regioregular polymers. Later, oxidative polymerization using iron,3 chloride produced higher molecular weight polymers but still lacked regioregularity. Subsequent advances in cross-coupling chemistry enabled the controlled synthesis of regioregular polymers. The McCullough method and the related Rika-Zink method improved regiocontrol but required cryogenic temperatures during metal-halogen exchange. GRIM polymerization simplified the process by allowing metal-halogen exchange at room temperature, making the synthesis more practical and scalable. General principles of GRIM polymerization. GRIM polymerization proceeds through 2 main stages: formation of organomagnesium thiophene intermediates via Grignard metathesis. Nickel-catalyzed cross-coupling polymerization to form the conjugated polymer chain. The method typically begins with 2,5-diBROMO3-alkyl thiophene, which reacts with a Grignard reagent such as T-butyl magnesium chloride to form a mixture of regioisomeric Grignard monomers. Despite the mixture of isomers, the nickel catalyst selectively incorporates the less sterically hindered species, resulting in a highly regioregular polymer. Step-by-step mechanism of GRIM polymerization. GRIM polymerization is closely related to Kamada cross-coupling reactions and is often described as Kamada Catalyst Transfer Polycondensation, KCTP. Step 1. Grignard metathesis. The process begins with the reaction of 2,5-diBROMO3-alkyl thiophene with a Grignard reagent. This reaction produces a mixture of organomagnesium thiophene intermediates. Step 2. Formation of the active nickel catalyst. A nickel catalyst, typically nickel, DPPP, Cl2, is introduced into the system. The catalyst undergoes reduction and coordination with the organomagnesium monomer to form an active nickel complex capable of oxidative addition. Step 3. Oxidative addition. The nickel catalyst inserts into the carbon-halogen bond of the thiophene monomer. This step forms an organonickel intermediate. Step 4. Transmetallation. The organomagnesium species transfers the thiophene group to the nickel center. This step prepares the complex for carbon-carbon bond formation. Step 5. Reductive elimination. The two aryl groups coupled to nickel undergo reductive elimination, forming a new C-C bond between thiophene units. The regenerated Ni catalyst remains coordinated to the growing polymer chain. Step 6. Catalyst transfer and chain growth. Unlike typical cross-coupling reactions, the nickel catalyst remains attached to the polymer chain end and migrates to the next monomer unit. This catalyst transfer mechanism allows chain growth to continue in a controlled, living-like manner. Living nature of Grimm polymerization. The catalyst transfer process results in several characteristics similar to living polymerization: predictable molecular weight, narrow molecular weight distribution, retention of active chain ends, ability to form block copolymers. Because the nickel catalyst remains associated with the chain end, further monomers can be added to extend the polymer chain. End group functionalization. One important advantage of Grimm polymerization is the ability to functionalize polymer chain ends. For example, allyl-terminated poly,3-hexylthiophene, can be produced by reacting the nickel-terminated polymer with allyl magnesium bromide. Such functionalized polymers can act as macroinitiators for other polymerization techniques. Block copolymer synthesis. Grimm-derived poly,3-hexylthiophene, can be combined with controlled radical polymerization techniques to produce block copolymers. Methods such as atom transfer radical polymerization, reversible addition fragmentation chain transfer polymerization, nitroxide-mediated polymerization have been used to create conjugated rod coil block copolymers containing poly,3-hexylthiophene. These structures enable tuning of morphology and electronic properties. Recent advancements in Grimm polymerization. Significant developments have expanded the capabilities of Grimm polymerization. Catalyst transfer polymerization, KCTP. Further mechanistic studies revealed that the nickel catalyst migrates along the growing polymer chain. This insight led to improved catalyst design and better control of polymerization. Improved catalyst systems. New nickel catalysts and ligands have been developed to enhance polymerization rate regioregularity tolerance to functional groups. These catalysts allow the synthesis of conjugated polymers with improved electronic properties. Continuous flow polymerization. Continuous flow reactors have been applied to Grimm polymerization to improve scalability and reproducibility in industrial polymer synthesis. Functional and donor acceptor polymers. Grimm polymerization has been extended to synthesize donor acceptor conjugated polymers, which are important materials for high-performance organic solar cells and electronic devices. Advanced block copolymer architectures. Recent work has enabled the preparation of rod-rod block copolymers, conjugated non-conjugated hybrid polymers, polymer brushes and nanostructured materials. Applications in organic electronics. Polymers synthesized through Grimm polymerization play key roles in organic electronic technologies. Major applications include organic photovoltaics, OPVs, regioregular poly,3-hexylthiophene, is widely used as a donor material in polymer solar cells. Organic field effect transistors, OFETs, high structural order and extended pi conjugation lead to efficient charge transport and improved hole mobility. Organic light-emitting diodes, OLEDs, conjugated polymers produced by Grimm polymerization can be tuned to emit light across a wide spectral range. Chemical sensors and flexible electronics. Solution processable conjugated polymers enable low-cost fabrication of flexible electronic devices and sensing platforms. Grignard Metathesis Polymerization represents one of the most important methods for synthesizing regioregular conjugated polymers. The process involves Grignard metathesis of diallothiophene monomers followed by nickel-catalyzed cross-coupling polymerization through a catalyst transfer mechanism. The technique provides excellent control over molecular weight, regioregularity, and polymer architecture, enabling the synthesis of advanced materials such as block copolymers and end-functionalized polymers. Recent advances in catalyst design, mechanistic understanding, and polymer architecture have further expanded the scope of Grimm polymerization. Because of its efficiency and versatility, Grignard polymerization continues to play a central role in the development of high-performance materials for organic electronics, energy technologies, and nanostructured polymer systems.